Good morning, dear students. This is Dr. Gunamardana, and today we will be discussing on this transaction. In the outline, what I am going to cover today, first is the transaction concept, then is the transaction real states, concurrent executions, serializability, recoverability, implementation of isolation, then transaction definition in SQL, testing for serializability. These are things we are going to cover. Now, let us have an idea about the concept of this transaction. Transaction is a unit of program execution that accesses and possibly updates various data items. For example, suppose we want to transfer an amount of $50 from account A to account B. So this is a transaction. So for this, remember A and B are two accounts. From account A, I want to transfer $50 to account B. Let it be initially A is having $1,000 and B is having $2,000. So how do we represent this transaction here? First step, read A, right? So it will be $1,000 and A is equal to A minus 50. It should be 950 and write A. So A should be 950. Similarly, read B. So B is equal to $2,000 and B is equal to B plus 50. It will be 2050 and write B. So again, it is 2050. What are the two main issues to deal with this transaction? First is failure of various kinds such as hardware failure and system crashes. So these are the two main issues. Second thing, concurrent execution of multiple transactions at the same time, more than one execution happening. Okay, these are the two main issues to deal with. Now, what is the required properties of a transaction? For what are the transactions we have seen last read A is equal to A minus 50, write A, read B, etc. All the times we have to follow the properties what we call the acid property. Acid property, the first A stands for the atomicity. It means that either the entire transaction is to be carried out or none of the transaction to be carried out. That means it has to roll back. No partial execution is allowed. For example, see, if the transaction fails after step 5, step 3, so write A, that is A minus 50, 950, but it fails. And before step 6, and it is not written in the step 6, what is the 50 deducted, that is added here, or withdrawn it is added here. So if it fails before this 6, then B still, it will show 2000 and A it will show 950, right? Then is the durability. You got it now? So either the entire transaction is to be carried out or it has to roll back. So partial execution is not allowed. That is the atomicity. Then is the durability. Suppose one of the user has been notified that the transaction has completed. That means for A, $50 already transferred. Then the updates to the database by the transaction must persist even there is a software or hardware failure. This is called durability. Even if there is a failure, once a transaction is carried out, 50 rupees is $50 is withdrawn, then it has to show what type of failure it may be. If it is not there, then it is not durable. Then coming to the consistency is the correctness. See, before transaction A plus B, it is $3,000. After the transaction A plus B should be also 3,000. Why? Because something is withdrawn from A, the same amount is added to B or deposited in B. It's clear. So because the amount is same is deducted and same is added. So the balance of A and balance of B, if we add, it should also be same as previous A plus B. So this is called consistency. Okay. So then the isolation. Is it A, C, I? Okay. A is for atomicity. D we already see, SIL, and I you are discussing now isolation. See, Suppose there are two transactions, T1 and T2. In T1, what is happening? Read A and deduct 50 from A, write A, read B, and deposit 50 with B, write B. So this is the transaction one. The transaction two, it is telling read A. Read A means after writing A, you have to read A, so it is 950. And read B, after writing you have to read B, so it is 2050. And print A plus B, it will be 3000. So, now isolation can be ensured trivially by running the transaction serially, that is one after the other. However, executing multiple transactions concurrently has significant benefits, as you will see later. Okay, so in that case, we find the problem. Then what is this isolation requirement? If between step 3 and 6 of the fund transfer transaction, another transaction T2 is allowed to access the partially updated databases, it will see inconsistency database. That means what I want to say, the transaction T2 is to be carried out, and you see here, this is there. If I read A, what is the value of A? A is equal to 950. What is the value of B? B is equal to 2000. What is A plus B? It is 2950. But actually it should be, why it is showing? Because by this time, this 50 is not added to B and it is not written also, not committed. That is the reason. So you have to make the transaction in such a way as if this happened in isolation, what the result it would have come, same thing comes if you are doing concurrently. Okay. Then like that, consistency, that is the execution of transaction in isolation preserves the consistency of the database. So these are the different properties. We call it as the acid property. This already we discussed in the class. Again, by this example, I will given what is atomicity, either the entire operation to be carried out or it has to roll back. Partially execution not allowed. Similarly, consistency, isolation, durability, we have given example. Now, we go for the various states or the transaction states. We have 5 number of states. One, the active state, then partially committed state, failed state, aborted state, and committed state. Active means the initial state, the transaction stage in that state while it is executing. That is the active state. Then partially committed, after the final statement has been executed, this is the partially committed. Failed means after the discovery that normal execution can no longer proceed, is the failed. Aborted means after the transaction has been rolled back and the database restored to the its prior state, this is called aborted. Okay, then start the transaction. You have to start from the beginning. What is the previous transaction? You have to carry. Committed means after successful completion. Then diagrammatically you can see this is the active state. Then from the active state, either it is going to partial committed or it is going to fail. So in the partially committed also it may fail. Say it may be a system crash, it may be power crash, whatever things are there. In the partial committed, then it can be committed means write B, write A, write B. Failed means it is aborted, again the transaction need to restart. So these are the 5 states. But remember, and you see the diagram, the various states are represented by circular things. And inside that you're writing active, partially committed, failed, committed, aborted. And arrow mark is there from active to partially committed, active to failed, partially committed to failed, partially committed to committed, and failed to aborted. Fine. Then we go for the concurrent execution. What is the concurrent execution? Multiple transactions are allowed to run concurrent at the same instance of time. Right. So what is the advantages? It increases the processor and the disk utilization. Okay. So that is the one of the, that means more number of process we can process in the single processor. Okay. Then it reduces the average response time in the operating system. You already studied response time it takes the first transaction to happen or the first process to start. Then concurrency control schemes mechanism to achieve the isolation. This is also achieved in the concurrent execution. Right. Then what is the schedule? Schedule, it is a sequence of instruction that specify the chronological order in which instruction of concurrent transactions are executed. It is just a process, sequence. Okay, first you do this, but then you do this, say first you read A, then withdraw 50 from A, then write A. So before that, if you read B and add A to B, that is inconsistent, right? And the transaction that successfully completed its execution will have a commit instructions at the last statement. So if the transaction fails successfully, then it has to abort and roll back. It has to start a new transaction. Now, let us do the same transactions with a schedule. What I told you that let T1 is the transaction which transfer $50 from A. Here the account A in the transaction T1 and the T2. Okay, this transfer $50 from A. It is deposited to B. This is the transaction. The second transaction, 10 percentage value of this A is deducted from A and the same 10 percentage is added to B. So these are the two transactions, right? So how do you represent read A? You see here, read A is equal to A minus 50, write A over committed here. Read B is equal to B plus 50, write B and commit. Once you commit, the value will be there. So any value or anything. Then same thing, the read A here it will be 950 and temp because whatever the in between data operations that we store with the temporary file temp. So temp is equal to A into 10 percentage. Then A is equal to A minus temp, write A and read B is equal to B plus temp, write B and commit. It's clear. So this is called the schedule in the order where writing. Okay. Now let us see another schedule. On the previous schedule, first we are executing T1, then we are going to T2. But here what we are doing, T2 is followed by T1. First I am executing T2. See, this is the order. You have to go like this and then it is coming like this. Then first read A. What is the value of A? A is coming 1000. 10 is equal to A into 10 percentage, 100. So A minus 100, that is 900, like that, 900 is 2100. Like that, you go for that one, right? So you see in the schedule 2, T2 is followed by T1 first. Can you see here? Then the previous case, T1 followed by T2. First T1 is executed, then T2. In this case, first T2 is executed, then it is followed by T1. Clear? Now, in the schedule 3, let T1, T2 be the transaction defined previously. The following schedule is not serial, but it is equivalent to schedule 1. So this is not serial. That means in the serial means what we are doing, all the operation of A we are completing first, then we are going for the operation of B. But here what we are doing, in the transaction T1, first read A and do the operation on A and write A. Then instead of going for this one, I'm starting read A, go for 10 because these are related to A. Once A is written here, then operation on A, we don't have any problem. It is up to this time, no problem. Then read B is equal to, because by this time, B we did not touch. So B will be 2000, 2000 plus 50, so 2050. Then read B is equal to, so this what you see here, this is the equivalent of T1. What is T1? T1 is this one. What is the schedule we prepared here? Schedule 1, and the next one is the schedule 2, and third one is the schedule 3. So schedule 1 and schedule 3 are equivalent. So you can write schedule 1 or schedule 3, the operation will be same and the output also will be same. And how do you say? Because A plus B value must be preserved. Before transaction A plus B was 3000, here after transaction also A plus B will be 3000, right? Now you go for the schedule 4. In the schedule 4, what I'm writing, read A is equal to A minus 50. Again read A, which value it will read? Because we have not written A, it is not committed. Then the same A value, 1000 also it will committed. You get it now? So this what we are writing it here, it does not preserve the sum of A plus B. So there will be a difference of $50 here. Got it? So this is not the equivalent schedule. Now, in the serializability, the basic assumption is that each transaction preserves database consistency. Correctness should be there. How to write the transaction, that is your thing. You make the equivalent of that one, but Finally, A plus B value should be same before transaction, after transaction. Thus, serial execution of a set of transaction preserves database. If you are doing serially or serial execution, then there is no problem. A possible concurrent schedule is serializable if it is equivalent to serial. So, is it possible that we do concurrent process or execution instead of a serial schedule? We do in such a way that it is equivalent to the serial schedule. Okay. So the different form of schedule available, equivalence is available. One is the conflict serializability, then is the view serializability. Right. So we ignore operations other than read and write instruction because these two are important. Either we are going for read or we are going for write. So we assume that transactions may perform arbitrary computations on data in local buffers in between read and writes. And our simplified schedules consist of only read and write. Other we are ignoring, other is not important for us, right? Then where is the conflict? See, if both are read, then there is no conflict. If one is read and one is write, so that is a conflict. First one is write and second one is read, that is also conflict. Because before the value is written, if you want to read, then you will get the incomplete data, vice versa. And if the both are right also, there is a conflict. You get it now? So these only where it does not conflict, that is if both the read operations, if you are going for II and ij, both you are reading, just you are reading the values, so there is nothing conflict. Then what is called this conflict serializability? If a schedule S can be transformed into a schedule S dash by a series of swapping, that means this operation is swapped here and there. Swapping, then we call it as a conflict equivalent. We call it as a conflict equivalent. We say that schedule S is conflict serializable if it's conflict equivalent to a series. So try to understand. If you are swapping, we call it a conflict because by swapping, it does not guarantee that the uh, no this consistency will be there. What he's telling, if you make a equivalent of that one, serial one, then it will be conflict serializable. If it is conflict equivalent to serial schedule. Right now, let us see. Now, this conflict serializability we are continuing. The schedule 3, what you have written it here, see it here, uh, can be transformed into schedule 6. So, see, this is the schedule 3. What is schedule 3? Read A, write A, then read A, write A, read B, write B, read B, write B. What is telling? See, read A, write A, then here I go for read B and write B, then I read A, write A, read B, write B. So if I go for this one, this schedule 6, okay? This is the just transformation of the schedule 3. What is there in schedule 3 in the left hand side? Same is the schedule 6. This is called a serial schedule, but T2 followed by T1 by a series of swap in non-conflict instruction. Therefore, schedule 3 is conflict serial. Right? Now, okay, these are things you go through. I don't think that much of things are there. Then we come across something like the cascading rollbacks. A single transaction failure leads to a series of transaction rollback. Considering the following schedule, when none of the transactions has yet committed, so the schedule is recoverable. See, so read A, read B, write A. Then again read A, write A, read A, and it has aborted. So if T10 fails, T1, T12 must also roll back. Why? Because T10 fails means it has not written A. Then you read A, wrong things it will come. Again T12, again it is not written, A is not written, again you are reading. So it will give a conflict things, right? Then what is the cascade schedule? So you see here, read A, read B, write A. Here B is not written, but A value will be correct. So then read A, write A, and here read A. Here what happens? For each pair of transactions Ti and Tj, such that T Tj reads a data item previously written by Tj. Here, A value is already written. So reading that A, it doesn't again conflict. And again it is writing A. Then T12, it is reading the value of A. So there is no conflict. Example of schedule that is not cascade based. Then concurrency control. These are the some of things you can. Then another item is there. We call it the view serialization. Let two schedules S and S dash with the same set of transaction S and S dash are view equivalent. The following three conditions are met with the data item Q. What is the three conditions? If in schedule S, transaction Ti reads the initial value of Q, then in schedule S dash also transaction Tj must read. Are you following me? So S is one schedule and S dash with the view equivalent. S dash is the view equivalent of that, right? Are getting so telling in schedule S, suppose Ti reads the value of key, then in S dash equivalent, schedule equivalent, also Tj must read the value of Q. Then second one, if in schedule S, transaction Tj executes read, so Ti execute reads, and that value was produced by the transaction Tj if any, then in schedule S dash also transaction Ti must read. So anyway, these are the three conditions. This is necessary for the view serializability. Third one, transactions that perform the finally write queue operations in schedule S must also perform the final write queue in view schedule, that is the S dash. Okay. So if these three conditions satisfied, then we call the view serializability. Right. So the same thing, more complex notation of serializability. It is written here. You can check it with all things. So with this, we conclude this chapter transaction. The first chapter of this transaction. The remaining we will cover in the next video. Till then, goodbye.